Imagine hearing this headline. A quantum company says it squeezed dozens of logical qubits out of just 98 physical qubits. And your first reaction is probably, okay, is that actually impressive, or is this just quantum computing word salad again? Because for years, quantum headlines have sounded like this strange mix of science fiction and marketing. More qubits, new record, quantum advantage, revolution is coming. And yet, for most people, the obvious question never really goes away. Can these machines actually do anything useful? And if not, what is the real bottleneck? That is why this new result from Quantinuum, announced on March 4, 2026, actually matters. Not because it means quantum computing is suddenly solved. It doesn't. But because it points directly at the part of the problem that matters most. Not how many qubits you have, but how many of them you can actually trust. And that gets us to one of the most important ideas in all of quantum computing, the difference between a physical qubit and a logical qubit. A physical qubit is the real hardware, an actual fragile quantum object inside the machine. Depending on the platform, that might be an ion, a superconducting circuit, an atom, or something else. But whatever form it takes, it has a huge problem. It is incredibly easy to disturb. Tiny amounts of noise, heat, vibration, stray electromagnetic effects, imperfect operations, all of that can push the qubit off course. And if the qubit is carrying part of your calculation, that means errors, lots of them. So a logical qubit is the workaround. Instead of trusting one fragile physical qubit by itself, you spread the information across multiple physical qubits in a carefully designed pattern. That way, the system can detect and, in some cases, correct some of the errors without destroying the quantum information you're trying to preserve. You can think of it like this. A physical qubit is like writing a message on a single soap bubble. A logical qubit is like encoding that same message across a whole formation of bubbles, with enough structure that if one gets distorted, you can still recover what the message was supposed to be. That is the basic dream of quantum error correction, and without it, large-scale useful quantum computing probably doesn't happen. This is why the Quantinuum result is getting attention. In its March 4th announcement, the company said it had demonstrated a low-overhead way to create up to 94 error-detected qubits and 48 error-corrected qubits from 98 physical qubits. It also said that with 64 logical qubits, it simulated quantum magnetism at a scale that can be very hard for classical computers. That sounds dense, so let's unpack it. First, error detected is not the same thing as error corrected. Error detected means the system can often notice that something went wrong. Error corrected goes further. It can actively fix at least some classes of errors and keep the computation alive. That distinction matters, because in quantum computing, simply knowing that an error happened is useful, but actually correcting it is much closer to the long-term goal of fault-tolerant computing, where a machine can keep going reliably as noise keeps trying to knock it off track. Second, the phrase low overhead is doing a lot of work here. In many discussions about quantum error correction, the scary part is the overhead. You don't just need one physical qubit for one useful qubit. You might need many, potentially a lot. That's why people sometimes talk about needing hundreds, thousands, or even more physical qubits to build a much smaller number of really reliable logical qubits. So if a company can reduce that overhead, if it can get more useful logical performance out of fewer physical qubits, that's a big deal. It doesn't mean the problem is solved, but it means the mountain may be less impossibly steep than it looked before. Third, Quantinuum also says these logical qubits achieved better than break-even fidelity against the physical qubits on several benchmarks. That phrase sounds pure jargon, but the basic idea is simple. If your error correction scheme takes a bunch of physical qubits and combines them into a logical qubit, but the logical qubit ends up performing worse than the raw physical hardware, then the whole exercise is kind of pointless. Break even is the moment when the protected logical version becomes at least as good as, and ideally better than, the physical qubits underneath. That's one of the milestones the field cares about most, because it suggests the protection is starting to pay for itself. Now, one really important caution here, this is still a company announcement. That doesn't mean it's false. But it does mean we should be precise. The right takeaway is not quantum computing is done, we won. The right takeaway is one of the hardest and most central problems in quantum computing, error correction with manageable overhead, appears to be moving forward in a meaningful way. And if that trend continues, it changes the timeline conversation. That broader shift is exactly why this story matters beyond one company. A recent Nature feature argued that a string of advances has made some researchers more optimistic that useful quantum computers could arrive within about a decade rather than many decades away. And one of the biggest reasons for that changing mood is progress in exactly this area, turning noisy hardware into more reliable logical computation. Even Reuters reporting last year on Denmark's planned magnet system centered on logical qubits as the threshold that might begin to unlock genuinely new science and chemistry applications. The industry conversation is no longer just who has the most qubits. It is increasingly who can make qubits useful enough to matter. And that shift is healthy, because raw qubit counts alone can be misleading. A machine with a lot of noisy qubits may still be less useful than a smaller machine with far better control, lower errors, and more effective logical protection. That is why this story is bigger than Quantinuum. It is really about the field itself growing up. The hype era was dominated by a simple scoreboard: more qubits equals better machine. But the harder truth is that quantum computing is not just a race to build bigger hardware. It's a race to build trustworthy computation out of untrustworthy parts. And that's a much deeper engineering problem. So what should you actually remember from this? Here's the simplest version. A quantum computer is powerful in theory because qubits can represent and manipulate information in ways classical bits cannot. But in practice, qubits are fragile. So the central challenge is not just creating qubits, it's protecting them well enough that they become useful. Quantinuum's March 4th result matters because it suggests a more efficient route toward that protection. The company says it demonstrated up to 94 error-detected qubits, 48 error-corrected qubits, and a 64 logical qubit quantum magnetism simulation using only 98 physical qubits. If those kinds of results keep improving and hold up under broader scrutiny, then the path to useful quantum machines starts looking more real, less mythical, and a lot closer to engineering than magic. And that may be the most important shift of all. Because the future of quantum computing may not arrive with one giant Hollywood moment. It may arrive through a quieter realization that the machines are finally becoming reliable enough to do work we actually care about. And when that happens, the biggest headline won't be how strange quantum computers are. It will be that they started becoming practical. If you found this useful, a like and subscribe helps us keep making more of these videos. Thanks for watching.